Hello everyone again and welcome to my channel. On our previous video we looked at the relationship between the electron count and geometry of a coordination complexes, and now this complexes with the formula MLX, where X is between 2 to 4 and M is the transition metal ion with specific d electron count, and this was actually considered in our way to see the relationship between the d electron count and that of the number of ligands attached to that particular transition metal ion in a complex. Now in this video we will continue from where we stopped, which is now moving ahead with X, which is X equals to 5. Now X equals 5 tells us that hey, we have a coordination number of 5, and with respect to the geometry, they, which is this complex, like for example nickel, which is attached to cyanide, not 1 not 2 but 5 cyanides, will have an overall charge of 3 minus. So in our way to find what the oxidation number of nickel is, we do know that nickel is added with cyanide charge, which is -1 times 5, which is equals to -5, and all this is equal to -3. Moving -5 over to the other side, what we get is nickel to be +2. So nickel loses 2 electrons from its 10 electrons to have a d electron count of 8. So what we recognize is that nickel does obey both two geometries. One geometry which is a trigonal bi-pyramidal, and while the other geometry is square base pyramidal. Now I'm going to draw both of them just for we to actually recognize this. And one of these, which is a trigonal bi-pyramidal, goes like this. The axial rotation is a C3 and the equatorial region is a C2 prime rotation in there, and we have our plane which is actually perpendicular to the principal axis of rotation, and the point group of this is D3H. Now on the other side here, which is the square base pyramidal, we have just one axial, and we have the equatorial, which is actually in the form of a square, and since we have one axial, then we have no sigma h because there's no mirror plane there. However, we have a sigma v and we have a C4 rotation in there, and in total we have a point group which is C4v. Now in this particular case, since nickel has D8, there's another important example which we are going to look at in here, and the important example is relating to how this compound behaves when it is in an NMR study. So this compound is actually iron carbon monoxide, and this is actually 5 of the carbon monoxide attached to this ion, where iron is actually D8 ion in here with 8 valence electrons, and carbon monoxide, they donate 5 lone pairs. So what happens is that once this donates 5 lone pairs of electrons to this ion system, what we have as the total number of electrons is 18 valence electrons in the overall coordination complex. Now this actually exhibits a trigonal bi-pyramidal geometry, and this geometry is actually drawn below, which is over here. So we have, so now what we recognize is that interestingly this geometry obeys the Berry Pseudo Notation, and this particular Berry Pseudo Notation occurs in NMR timescale for the 13C or carbon 13 NMR spectrum. Thus actually exhibits one signal due to rapid interchange between the axial and the equatorial positions of our carbon monoxide. Therefore, at low temperature, the C13 NMR does reveal one signal. However, at high temperature, the C13 NMR spectrum shows two signals, and these two signals are in a 3:2 ratio, and this ratio is caused by the Berry Pseudo Notation, because at high temperature there is an interchange between the axial and equatorial positioning of our CO bond, and also high temperatures increases the kinetic energy that causes this nice transition between the axial and equatorial positions, where if I want to draw it over here, we can have our axials here and we have our equatorial, which are the key ones we're going to focus on in here. And what we notice is that this equatorial position, they have 120-degree angle rotation now angle between them, and what we notice is that once this bond is bending inward over here, this bond for the equatorial is bending outward, and our B bond over here to increase in angle, getting closer to 180 degrees or approaching 180 degrees, which is from here to here. And finally, what we have is that our A, which is the axial positions, later approaches 120 degrees, while this is our equatorial. And this is actually equivalent to, let me make this E and make this E, so that you'll be able to notice this really well. And what we have as a result is our changing of the positions of our axial with respect to our equatorial positions of our CO molecules that is attached to our specific transition metal over here, which is iron. So that's about it for this particular explanation of Berry Pseudo Notations with respect to C13 NMR studies at high temperature versus that at low temperature. All the same, thanks for following me through this. Truly appreciate it. On our next video, we're going to look at Cn equals 6, which is going to be more relating to increasing the interactions and also the coordination number of our coordination complex in there. Thanks for watching. Please hit the comment down below, let me hear your thoughts. Hit the like, share and subscribe. By that way I can talk to you all later. Be smart.